Okay, welcome everyone. Thanks for joining the Manchester Java community today. First off, I'd like to say thanks to our sponsor, RecWorks, who pay the meetup fees for the Manchester Java community. We really appreciate this, so thanks to them for providing this sponsorship. So today, we're joined by Nicolai Parlog from Oracle, who is a Java developer advocate. So thanks for joining us today, Nicolai.
Sure.
As we've kind of mentioned earlier, if anyone has any questions, just pop them into the chat box in Zoom, and we'll try and monitor them between myself, Nicolai, and Nick and Craig, I think I saw. Okay, so I'll hand over to you, Nicolai. Thank you very much.
Yeah, first, Jonathan, Nick, thank you for having me. I'm very enthused to be there. I'm coming originally from Dortmund, which is also a very industrial city. So I think where I grew up has some similarities to Manchester. And it's a shame that we can't come visit, but maybe we can do that, I don't know, like next year, in 5 years. Who knows when travel will be possible again. Yeah, so I'm Nicolai. I used to just talk about Java as a hobby. But apparently I did it well enough that Oracle decided to hire me. So that's what I do now. So I'm a developer advocate at Oracle. And yeah, I want to talk to you. But I created this talk before I started there, or at least I started working on it. So when I talk about why don't they just, they are now my colleagues. So I have to tone down the criticism. But also, that was actually the original intent was, well, sometimes you type, you get frustrated. Why is Java so complicated? Like, if we just have this feature, why don't they just do X, Y, Z, and everything would be so much better? And occasionally I had these, well, I often have these thoughts. Occasionally I follow up on them. And then it turns out there's actually a good reason. Like, in many cases, there are reasons. We don't have to agree to all of them, but it's not just laziness. There's more behind that. And so I created this talk to explore those spaces, like where things seem to be like Java seems to behave in a way that could be so much better if just this one thing were different. And so the specific word "just" I want to explore, because it's usually not just that simple. Okay, so I want to go through these 5 things in general. I'm not sure whether we can cover all 5 of them today. If push comes to shove, I'm going to kick one of them out. I'm not sure exactly how much time we have. I think it's a lunch break for most of you, so I don't want to, stress too much of your time. I'll just keep going, and Nick or Jonathan will at some point just tell me to shut up, and I will. I promise. Okay, so let's start with fields. Why don't they just let us add fields to records? So look, wouldn't this be great? I can here create. Should I zoom in a bit more? There you go. I want to create a record, like we always do since Java 16, right? With the component name, but I also want to give it an ID, and I want to hide that ID internally. But damn, records don't let me do this. I can't. It's giving me a compile error. I cannot have I can't have additional fields in here. So why would I want to do this? Well, obviously, I want to benefit from encapsulation by having an additional private field without accessor, and I also want to benefit from boilerplate reduction. But the thing is, records are about neither. Both encapsulation and boilerplate are things that records touch on, but are not at all core to their mission. And once we understand that, we can better understand why we cannot add fields. So the record semantics are, records are classes that act as transparent carriers for immutable data. We're going to mostly focus on transparency here. And also, this also answers, by the way, why fields are always final, the mutable data part. But we're going to focus on the transparent part here. So the transparency inspires kind of a motto that you can read up in one of the early in the design documents, which says, the API for a record models the state, the whole state, and nothing but the state. And this kind of motto, this kind of limitations, or this motto implies certain limitations or restrictions. So if the API should model the state, then I need an accessor for each component. I need an accessible constructor with 1 parameter per component. I have a record that takes a first name and a last name. Then I need a constructor that has both of these. Otherwise, the API doesn't model the state. If I can have additional fields, then the API would not model the whole state. It would just model part of the state. So that's why I can have additional fields. And for similar reasons, I can have class inheritance. So now I basically answered with, well, because of the motto, we can't have private fields or additional fields, but that just kicks the can down the road. So what's up with the motto then? That seems to be an arbitrary decision at this point. So records were designed to be nominal tuples. Nominal means that they are identified by their names, as is common in Java. In Java, everything is identified by its names. There are other type systems out there that use structural typing, TypeScript, for example, where if two things have the same structure, they're interchangeable, which makes for a fun development experience if you're not used to it. But in Java, things are identified by their name. So that's totally normal. That's nothing special to records. The interesting part here is tuples. Tuples are mathematical concepts, and you know them already. In school, you write like two-dimensional points as x, y, or three-dimensional points as x, y, z. Those are tuples. And for a tuple to be a tuple, or for a type rather to be a tuple, it has to conform to these restrictions. Imagine you had a three-dimensional point in math, but you could only access the first two dimensions. That would not even make sense, really, right? And so for a type to be a tuple, it must follow these restrictions. I linked to a blog post here that goes a little bit deeper on the math. But just a little bit, so that you can look into if you're interested. So now I kicked the can further down the road. I said, okay, we have these restrictions. The model, the API must model the state, the whole state, and nothing but the state, because they're supposed to be tuples. Okay, but why tuples then? And here we get to the core of this. If you have tuples, certain things, specifically deconstruction, becomes easy and lossless. And that gives us a few cool things that we can do with this. The first thing is what JEP 405 proposes, which are called record patterns. And they deconstruct a record. So since Java 14, I want to say, or 16, these are finalized. The instance of check, well, instance of check, of course, that's old, right? So you can always check whether range is an instance of range. But what you can do additionally, since Java 16, is you can add a name here. Instead of this thing, you can just add a variable name, and then you get the check, is it really of that type? And then it gets assigned to a variable of that name, and they can use that. But what JEP 405 proposes on top of that is that you can deconstruct this record in this case. So what I'm saying here is, well, if range is, if this variable range is an instance of the type range, I will take it apart into low and high. And I'm quickly going to check whether high is lower than low, which it probably shouldn't be. And then I'm returning a new range that has these two variables flipped. The specific logic isn't that important. What's important is I take the record apart and put it back together. And I can be 100% sure that there was no hidden state that was lost. Range cannot have a private string field that's an ID, for example, that gets lost in this transformation. Because records guarantee that I can see the entire state. So these kinds of things where you take an instance apart and put it back together would not be guaranteed correct if you could have hidden state. You can drive this point further into this feature, which at this point is mostly fictional. There's not even a JEP. I'm not even aware of a mailing list discussion. So this is, it might not realize at all, but this is something that you can do if you have this lossless deconstruction and reconstruction. Imagine you have a range that goes from 5 to 10. And what you want to have is one that has the same upper value, but a different lower value. And what you would do if this were a POJO, you would probably call set. Set lower, and then you mutate the state, which is, you know, like, it's kind of common in Java, but it's not exactly great. At least I try to avoid it as much as possible. What you could then have is, well, can range have a method that is maybe not called set low, but with low, where you pass 0 and then you get a new range back that, you know, has just low changed. You could type these methods out. They're sometimes called withers, you know, similarly to setters and getters. But these are still methods that would have to be generated either by the compiler or by your IDE. But what if we can host it into the language? What if we create a new keyword with, and what that does is it takes this record, it deconstructs it into low and high, because we know that's that this is all the state that the range has. Then we reassign whatever we want in this block. And by the end of this block, this gets passed to the compiler, and we just put it back together, and we get a new range from 0 to 10. So this would be a language construct that builds on the assumption that records can be taken apart and put back together without losing anything, that you can always get all the things you need to reconstruct the object. So that would be pretty cool. That would mean that we have basically these withers on the language level, which would also make them, for example, more performant, right? If you have like 8 properties, you want to change 4 of them, you can just go with, and then you set 4 of them. This could partially at least replace certain construction patterns, like maybe the builder pattern. This would be really nifty. So interesting to see where this is going. And the third one I have is serialization. And this benefit is already materialized because the transparency makes serializing and deserializing records much easier. That means, for the most part, that it's easier to implement and maintain in the JDK, but also in other libraries that construct and deconstruct stuff, for example, to put it into JSON or to parse it from XML. All of that, they also need to use reflection to take classes apart or put them together. And with records, this is much simpler. But it's also easier for us because we know that now all construction goes through the constructor, because there's a guaranteed constructor that takes all the elements. And that means that always the constructor can get called, unlike in real, like normal serialization, where when you deserialize, you have to know some magic methods that you have to implement in a non-obvious way to make sure that, for example, invariants that the constructor should check are actually checked. That makes it safer. And it makes it a bit faster because there's like less special casing. It's actually pretty straightforward to serialize or deserialize a record. If you're interested in more on this, there's the Inside Java podcast episode 14, that goes into this specific topic. Okay, so as a summary, records want to be nominal tuples, and that requires transparency, and that transparency requires that there can't be additional fields. And if we have that transparency, then we can do stuff like destructuring, we may get these with blocks, we get better serialization, and maybe more things down the road. So that's the specific reason why records don't allow fields, which is a very specific complaint that I just addressed, and you might or might not have had that. But there are things that we can learn from that in more general, on a higher level. And that is that it can make sense to introduce specific restrictions if those restrictions enable other features. So not every restriction is a reduction of the overall feature set. A restriction or limitation over here can enable or open up other features elsewhere. So in total, you might get more out of it. Or even if it's not a strict comparison of less or more, you might get something new out of it, something that was not easily possible. So with classes, you have the full flexibility, you have encapsulation. If you need that, use a class. Records give you a different trade-off, which you can then use in these different circumstances. That's it on records. As we said before, if you have any questions, put them into the chat. I also seem to have skipped, there you go, there's the link to the slides. I want to quickly put that into the chat. You can just move along, use page up, page down to navigate. That works best. And then you can, look at the slides while I go. If you don't have any questions, I would just go on to talk about streams and checked exceptions. Okay then. So why don't they just let streams handle checked exceptions? Oh boy, that's a fun one. We're going to look at a lot of code. Probably the only one where we're going to look at a lot of code. But it's an interesting one because, like, I don't know, it didn't annoy me too much. I'm not the biggest user of checked exceptions. I mean, I do use them, of course, but I always, played around with other ways to show errors that don't necessarily use exceptions. But still, it's annoying. So at some point, I sat down. I was like, okay, let's do this. How hard can this be? Let's try to write a stream pipeline. A stream API that works with exceptions. Okay, so what do you want? Well, let's say we have these two methods here. We have one that computes, it turns a string into an int, but it can't throw an IO exception. We have another one that supercharges an integer, it returns a supercharged integer, whatever that is, and can throw an interrupted exception. So now we start with the stream of foo and bar. We want to compute, we want to supercharge, and then we want to turn it into a list. And obviously, these two methods can throw exceptions, so I want to do a try-catch block where we catch these two exceptions. So that would be the goal. Okay, so let's do this. The first thing we need is we need to create an function interface that can throw exceptions. And the other thing is we need to change the stream API somehow so that they throw exceptions. Okay, first attempt, straightforward. Let's create a new function that takes two type parameters. One of them is the input type, one of them is the output type, and it can throw an exception. And then I have this super simplified stream interface, which consists of a map function and a toList function and nothing else. But all of this generalizes to filter and flat map and collect and reduce. The important part is we have one intermediate operation here and one terminal operation here. Okay, so I'm giving this throwing function to map, so let's have map throw that function. Straightforward. The problem is that's not correct at all. Because streams are lazy, map does not apply the function. The terminal operation applies the function. That means the terminal operation has to declare that it throws. This is actually the underlying core issue which we'll not be able to solve. So let's keep that in mind. Streams are lazy, so that means when I pass something that throws an exception to map, map will never throw that exception. It will always be the terminal operation. Okay, easy. Let's just move throws exception down here then. That's what we want to do then, right? And yeah, that kind of works. So if I could do a stream of foobar, do compute and supercharge and toList, then toList declares that it throws an exception, and I'm getting there. There's like a part of the path is done. But now what exception do I catch here? Well, I don't really know, right? The API just says throws exception, so I don't know which exceptions I have to throw. I have to actually look into compute and supercharge to figure it out, and then I'm still left with everything else. And even worse, if my map doesn't throw an exception, well, toList says it throws, so I still have to handle it. I still have to catch it down here. So this would actually be a compile error. So that's really awful. The compiler doesn't know which exception type. We have to catch the general exception and figure out what exactly would be going on or could possibly be going on. And we always have to catch that exception, not just in the rare case where the pipeline actually throws, but in all cases. So we need something more specific than exception. Just exception is obviously not enough. Okay, attempt number 3. Let's pull in generics. I'm not sure whether everybody's aware of this, but what you can do in Java is when you declare a variable, a type variable, like in and out, you can limit what types it can be. This in and out, they can be everything, but X can't be everything. It must be some kind of exception. And if you do that, then you can actually throw this generic type. So Java does have generics for exceptions. Okay, so let's do this. Let's have a function that has a third parameter, which encodes which exception it throws. And then we add this type also to the stream. So the stream always knows which exception it's supposed to throw. So it knows at some point it's a stream of runtime exception or a stream of IO exception. And then toList will throw that kind of exception. And what does map do? Well, if you give me something that throws the function exception type, I'm going to return a stream that throws the function exception type. Okay, let's give this a go. Let's try this. I start with my stream of foobar, and then I do compute. Compute throws an IO exception. So I get a stream of integer that can throw an IO exception. Now I supercharge, and now it's an interrupted exception. And now I can catch that, so that's good. But I can't catch IO exception, because it isn't declared, right? We kind of lost it. This step here made us lose the information that our exception is also being thrown. So this catch block doesn't work. Oh yeah, by the way, in case you don't know, in Java you cannot catch a checked exception if it is not declared. Or maybe if a super type is declared, it works. But in this case, where only interrupted exception is declared as being thrown, you cannot catch the IO exception because the compiler is like, hey, we're doing checked exceptions. I have no reason to assume that they can be thrown here, so surely this must be an implementation error. So that's why it's a compile error. Okay, so that's not correct. Currently, we only capture the last function's exception. That's not enough. So we need to deal with the other ones as well. Okay, now it gets a little bit weird. What we're doing here in attempt number 4 is we need to create a static method map. That's unfortunate, but this trick that we're doing now does not work if map is not a static function. But what is the trick? Okay, so this static function declares the in and the out parameter as before. It gets a stream that takes the in, or that contains in, and returns a stream that contains out. So far, so simple. Now it creates a type that is called newx, which is some kind of exception. And that will be the type of the exception that is returned. But it has 2 more exception types. Both of them are below newx, And those are the exception types that the stream already throws and that the function already throws. So what this means is, say the stream throws this stream x and the function throws this fx. Then we're looking for a type new x that is a super type to both that we can then throw. So we're looking for what is a type of exception that encapsulates the two kinds of exceptions that are in play here. Stream throws the one, the new function can throw the other. What kind of exception works with both? I'm not gonna go through all of this in detail because that's really weird. Like, it looks really different from before because this is all a static map call that we have to do. We have to do some complicated nesting. What I want to point your eyes towards is the kind of exceptions that are being used. So this is different functions. This one throws what is this? A file not found exception, and this one throws a zip exception. And they're actually both IO exceptions, which is pretty cool. So this actually works. Like, we can throw a file not found exception here and throw a zip exception here, and then the toList will declare that it throws an IO exception, and then we can catch that IO exception. Still kind of weird that we don't know which specific exceptions we want to deal with, but it's definitely a step in the right direction. The problem is that this doesn't generalize very well. I mean, there are deep exception hierarchies, that's true, but it's very common that you have unrelated exceptions, and then this doesn't work at all. Like, even the initial example that we had, compute throws an IO exception and supercharge throws an interrupted exception. Guess what their common supertype is? Just exception. So that doesn't really help. Like, we're very quickly, we're back to the what was like the second attempt, where we just have to generally catch exception. So the common case sucks because we still have to lug around this runtime exception thing, which I didn't mention earlier, but some parameter needs to be here. So it's runtime exception then, apparently, because that's at least allowed to catch that. Writing stream pipelines, if everything is a static function, is horrible, and capturing exceptions in general just was already bad on the second attempt. James, yeah, I'm glad you're learning something about generics. That's not a trivial field. There's always more to learn there, and I'm still often stumped by the generics errors that I get. Even though I feel like I know them fairly well, there's always much more to learn. Okay, so somehow we have to keep the exception types distinct. So it doesn't work, like merging them doesn't work. We have to keep them distinct. And a simple way to do that is to just create multiple stream interfaces. We start with the stream interface we already know. But if you give me a mapping function that throws an exception, I'm going to give you back a stream that's called stream x1, which contains, the type that the function maps to, but it also has one generic parameter for this exception. And because this stream doesn't lug an exception around with it, toList doesn't throw. So okay, let's look at stream x1 then. Stream x1 has one exception type, and toList throws that one exception type. Makes sense. Now, if you map with a function that has another exception type, I'm going to give you back a stream x2, which apparently has two exception types in its signature. So okay then, stream x2 has two of those. Once again, the toList method throws both of them. Makes sense. But then with map, what do I do? How far do we go? Do we go up to 5, up to 10? I decided that I don't care anymore, and I just had a stream xn here, and that just fallbacks to throw an exception, because that's always the catch-all for everything. Okay, if we try this out, this actually works really well. So we start with the stream. We have a stream of string initially. Then we compute, which throws an IO exception. So now we get a stream of x1 of integer that can throw an IO exception. And if we supercharge, then we get a stream of x2, which contains integers, but can throw either this or this exception. And then both of these are declared on toList, and we can capture both of these. And we have to. The compiler will say, look, this throws IO exception or interrupted exception, you have to catch both. This is really good. This works really well. So this is correct and usable. For the fifth attempt was the first one that achieved that. But it leads to a number of additional interfaces, right? We need stream x1, x2, at least I would guess probably 0, 1, 2, 3, and n. Those are probably the 5 cases that we need. At least 5 cases we need. But remember that there are also primitive specializations, right? You have stream, and then you have long stream, in stream, and double stream, right? So that's another dimension. So that's already 4 times 5. That's already 20 interfaces. That's not good. And if we look at the methods, we realize, okay, some functions all the functions we looked at so far throw 1 exceptions. But of course, methods can throw multiple exceptions. So functions could potentially also throw multiple exceptions. So that would mean we need to have like map that takes a function with 1 exception and another map that takes a function with 2 exceptions. And then, it like goes from stream x1 to stream x3. So that's like we also explode number of stream interfaces, and within each stream interface, we explode the number of functions that we have in there, or methods rather. And all of them, right? There's then a map 1 exception, map 2 exception. There is a filter for all 3 of these. So they're like tons of overloads. Now, what we would actually need is variadic generics. And just so, like, I want to point this out beforehand, this does not work, but like I want to show you how nice it would be if it would. So imagine we could do something like var args, but for generic type parameters. Basically what I'm saying is I have an unknown number of types here, but they all extend exception. And then, I would just apply them, would just throw them. And now my cool stream interface would just say, okay, given I already have all of these exceptions that I throw, could be 0, could be a gazillion, and you give me a function that throws a bunch more, well, I'm just going to give you back a stream that just combines these somehow. I use an OR here. It's made up syntax anyway, so why not? So then you just put them somehow together, and then that would work. And that's great. That would actually do the trick very, very neatly. This is like the same situation we had in the previous attempt, but it's all on the same interface, so we avoid this explosion of code. But as I already mentioned, the kind of like small downside is that it doesn't work in Java, and nothing of that compiles. So that's not great. So there is a good solution out there. It's just unachievable at the moment. And attempt number 7 would be, screw that. We just deal with it the way the function programmers deal with it. We use something like a try or like an either, or we can filter errors out. We can use an optional. There are plenty of ways to deal with these situations. They have similar trade-offs or similar shortcomings as some of the attempts we already looked at. But it does work, and it works today without anything else. I have a link to another slide deck here where I explain that in a bit more detail. But the gist is these functions don't throw. They're not allowed to throw. What they must do is they must return, for example, a try, which means, hey, this is supposed to be an integer, but maybe it failed, in which case it's just a random error. So that's what this try does. So you encapsulate the fact that you can have an error in the return value, but in a way that it has methods and allows you to interact with it quite cleanly. So to summarize this, the problem with stream is that laziness splits the function that can throw an exception, the way you pass that and where that is executed, that those are 2 different places in the code. And the classic try-catch doesn't really work with that. We would need generics to carry exceptions from this intermediate operation to the terminal operation. And today's Java just contains no good solution, or let's say no perfect solution, but there are acceptable alternatives that you can already use and that are not worse than baking something into the language. And now taking a step backwards, I think it doesn't make sense to include something in the platform that does have serious shortcomings, all of what we discussed before, and then also, because that's then the solution, that's then the way code is written, it either limits or outright prevents which future solutions, if the language should evolve, which solutions could then apply. So I'm not saying we're getting variadic generics. I have no idea whether that's even realistic, but I'm just saying if you create a solution now, then you're probably not going to create a second solution later. And if the solution now is bad, that's not helpful. Particularly if acceptable alternatives already exists. So just because something isn't perfect doesn't mean that every fix, particularly not if the fix is somewhat partial, should be implemented. Some things are just suboptimal, but they're waiting for a better solution to be available in the future. Oh, James, yeah, exactly. I think what you described there is pretty much my attempt 6, yeah. I called them variadic generics. Yeah, I think I think what you described is probably ends up being the same thing, right? Okay. Unless there are questions about this, I'm just going to go on. The next ones are less code. I'm going to talk about immutable collections and why we can't have any, which is sad. Really, it's making me sad. Okay, so what do we want? I want immutable collections, but not just collections that don't have add methods. I want interfaces that express that this type is immutable and that guarantee that no mutation can occur. And I'm going to contrast that with what I call unmodifiable collections, which are just interfaces without any mutating methods or mutating methods that throw exceptions. Right? So one of them says guaranteed immutability. The other one just says, well, you can't modify me. Those are not the same thing. We'll see later what role this plays. And I like the other two things that I described. I do not want records to have fields. I can understand why streams don't handle exceptions, and I think there is no good solution to put into the platform, and I'm okay with the solution that we can come up with. You know, this like try and either types from more functional programming. But this one really irks me. I really want to have immutable collections. It's like so sad. Yes, here's my idea why this doesn't work. Okay, we're going to work on this example of a list. So the same applies to set and map and everything else. So let's take the list. Let's create an example, an interface immutable list, and we're just gonna say it's exactly like list today, but there won't be any mutating methods. They're all out. They're not part of that interface. So now we have a list and an immutable list interface. How do they relate? Well, let's try with making immutable list the super type to list. That's pretty good because then immutable list on the left-hand side here can have all the reading methods, and then list on the right-hand side can add all the mutating methods like clear and remove. So that's straightforward. Immutable list is a really clean interface that has the method that you would expect. The problem with that is that the way this type relationship works, you can sneak in stuff into an immutable list. So I'm creating a list of agents here, which is mutable, right? Array list is mutable, and the list here is also a mutable interface. I create an immutable list of agents, and I assign the one that I just created to it. And that works because immutable list is a super type of list. Now, if I look into this immutable list's elements, I will get no elements out because, there aren't any. So that's great. Now I take the immutable list and put something in. And now I take the immutable list, which is the same instance, just under a weaker interface. And now if I iterate over it, I get something out of it, which I really want to. So that's in general a situation that can happen with immutability. You might expect something to be immutable because you cannot change it, but that doesn't mean that other people can change it. This is what I would rather call like unmodifiable or unmodifiable view. This is also what collections.unmodifiable list do. They take a list that somebody can mutate, and they give you back a wrapper around it that you cannot mutate, but that doesn't mean that others can't. That's also right when you want to do when you want to put collections into fields, why you maybe want to do defensive copying. Because if somebody gives you a list and you just assign it to a field, the code that gave you the list, it might still be changing that list without you wanting it to, but you can't stop that. What you can do is create a copy. Anyway, long story short, if immutable list is the super type to list, I can change the immutable list, so that's not good. Okay, let's try it the other way around then. Immutable list now extends list. That has the downside that we have to cross out all these types, all these methods. Somehow you can't get rid of them, but you have to then deprecate them at least. But the good part is immutable list isn't extended, so it's really actually immutable. But the bad part is immutable list still has mutating methods, and though they declare that they throw exceptions. And immutable lists they can be passed as lists. So in most Java programs, it's kind of reasonable to assume that if you get a list, you're allowed to mutate it. And then if you start passing around immutable lists instead of lists, then you will end up with runtime exceptions where people get a list that they thought was immutable, thought was mutable, but isn't actually. So this is basically the situation we have with, for example, Guava or other libraries that offer immutable collections. They did the best they could. They created an interface, or rather an implementation, of the list interface that is definitely immutable. It throws exceptions on the methods that that would mutate the data structure. By the way, the JDK itself does it as well when you use the list of, for example. It's basically the same approach. And if your entire code base is built around the concept of immutability, then that works. But if it's not, you will occasionally have, or frequently have, this problem that somebody gives you a list that you think is mutable, but it's not. So as soon as it crosses API boundaries, this is not going well anymore, because then something is immutable, but you can't tell that it is. So the problem with this that we make is that we basically interpreted immutability as an absence. We took a list, removed the mutating methods, and that's all we needed to do. But that's not true. I want to call this an unmodifiable list. This is just a list that you don't know how to mutate. That doesn't mean it's immutable, right? That was the problem we had in the first situation. So let's call a list without mutating methods an unmodifiable list. I take an unmodifiable list, which has no add method, no clear method, and now I can do two things. I can either add the methods that I need to make it a mutable list, or I could add the guarantees that nobody will do that, and thus create an immutable list. So if we look at this from this angle, then immutability is a feature. You take a data structure and you add immutability as a feature to it, or you add mutability as a feature to it. And that also explains why it blew up in the past. Because types inherit features from other types. That's basically what the Liskov substitution principle boils down to, right? A subtype should be able to replace a supertype with it, and all the relevant behavior should stay the same. So if one of the two types is mutable or immutable, it inherits that to its subtype, and then that subtype wants to do both, and that's why it blows up. That's why there was never a good solution. So as I like to put it, immutability is not an absence of mutation, it's a guarantee there won't be mutation. And that doesn't work well together with mutability. So what we need to do instead is, immutable list or list cannot extend one another. We need both of them to extend some other type. So we take the unmodifiable list, which has all the reading methods, we create a list out of it, which adds all the mutating methods, and we also create an immutable list that extends unmodifiable list that does nothing but promise nobody will mutate me. Now, if we do this in practice, it could look like this. This makes some sense why these methods accept or return these kind of lists, but the details don't matter. Well, it's all made up, right? But the point is, what matters here is I have three types of exceptions, of lists, and I pass them here, and I receive them here. That's what I want to have, right? I want to be able to pass these new kinds of lists, and I want to receive them from methods. Straightforward. The problem is, code like this already exists, and it probably looks like this. Right? Because we already wrote a couple lines of Java code that are out there. I heard there are a few dozen Java developers, so some couple 100,000 lines probably were already written. And that means that most of them will probably take these types. They shouldn't always. Sometimes you can just accept a collection. I like to return streams. But, I think it's reasonable to assume that at least a bunch of code, probably the majority, looks like this, just takes and returns lists. So this is what we have. And now we want to go to that other case where we, use the new collections. Because if we want to benefit from them, we kind of have to use them. And specifically our code, but also our libraries and the JDK as well, right? So now let's look into how we can replace these types with one another. Let's say you have a list somewhere and you want to turn this into an immutable list. Well, those types are not directly related. So that's source incompatible, that requires rewriting code. It's not great. Okay, what if you do a return type from list to immutable, unmodifiable list? Well, now you're giving back a more general type that also doesn't compile. Once again, you have to rewrite code. But even in the case where you think, haha, my method accepted a list, and now I widen that to unmodifiable list. So now I accept a more general type. Surely that should work, right? You don't need to rewrite code, but you need to recompile code. Because when code compiles, it says, I'm going to call that method with that name and those arguments. And if you change the list of arguments, and these are two different artifacts, so two different jars, and one of them changes a method signature, then the bytecode over in that other jar will be like, well, I'm supposed to call method XYZ that takes a list, but it won't find it because now it's compiled to contain get an unmodifiable list. So that sounds like a lot of rewriting and even more recompiling. And now we have to do this for the JDK, all libraries, all frameworks, and our own code. That's not great. You could come up with alternatives like, okay, let's just duplicate all the methods. So for every method that you have that deals with exceptions, we're now going to create a second one that takes and returns the new types, deprecate the old ones, eventually remove them. Both of those would take forever. So as unfortunate as it is, I don't see a way how this works out reasonably well. So immutable collections are a great thing to have, but proper implementations of these types cannot extend one another. You need an additional supertype. And even before that, even if you could make one extend the other, there would not be a good migration path, but at least there would be some migration path. But this effectively requires rewriting, recompiling a ton of code across the entire Java ecosystem. And despite what you may think about the compatibility issues you had with Java 9, that would be a picnic compared to this. If we take a step back again and look at this from a higher level, I would say that any solution, anything that you have in mind that requires rewriting or recompiling the world, that split the ecosystem into basically like an old and a new kind of, well, they use the old collections, we use the new collection. And all of that for rather incremental benefits doesn't sound like it's worth it to me. Because the benefits are not exactly game changers, right? Like it would be good with immutable collections. I think it would be hard to find somebody who, well, not hard, but I believe that more than most people, that would be great to have them. But just because it's nice to have them, so be in a situation where they are there and all the code uses them, does not mean that it's nice to get them, that from where we are now to where we need to be, that there's a good path. Because sometimes there just isn't. And so it's not enough to look at the feature and say, well, if we had that, and it would, that would be perfect. You also have to look at from where we are to where we want to be. Is there a good path that takes us there? And there often isn't. Okay, Nick, Jonathan, I want to ask, do we have time for more? I have a little bit of a summary at the end. We could ask more questions at the end, but I also have 2 more topics, which let's say 10 minutes each. Should we go into one of these?
Yeah, I mean, I think I'd say there's time for one. If for 10 minutes each, probably one more topic, and then we've got 5-10 minutes at the end to see if there's any questions. Sounds good.
Okay, great. So let's start with null-safe member selection. What we want to do is to more easily chain method calls if something could be null. So like if you are in a situation where basically anything can be or return null, then code starts to look somewhat roundabout. I'm trying to avoid the word ugly, but I think it would be ugly. So, okay, so we have a street here that could or could not be null. Oh, sorry, no, we assign null. I'm stupid. We have a customer here that could or could not be null. And it has an address method that might return null. And that address returns a street. And what we really want to do is call customer, address, street. But each of those 2 could be null. And so we have to check for that to avoid null pointer exceptions. We could use it with the optional pipeline, which I personally think is much better than this. For a variety of reasons, and I would always do in this case if there's no way around everything being possibly absent. In that situation, would say, okay, customer is an optional now. The address returns an optional, so I need to flat map. And the street returns an optional, so I need to flat map that as well. And I get an optional string of street. That's okay-ish. Better yet, try to avoid that all kinds of things could be absent. But apparently we're in a situation where that's the case. So wouldn't this be nice? Just like use question mark dot, and then that's easy, right? Customer could be null. If it is null, all of this gets ignored, and the result of all of this is just null. But if it's not null, we do the thing. So in this case, we call address. And then do the same again. Like, is address null? If yes, this entire result is null. But if it's not null, then this resolves to, okay, let's now call street. And then we get that back. So that's like a simple one-liner. It's basically like the normal calls, just with some question marks in there. That's pretty cool. But I thought, like, this came up in some Twitter conversation, and I thought it was worth thinking about this a little more. So I wrote a blog post about this a couple of years ago, which is exactly the thought process that I present here now. So let's start to think this through. So where does null appear? How does it come into the world? And there are roughly two big buckets where you can put occurrences of null into. The first one is it's intentional. Here null is allowed. Something was not entered by the user, something is not yet initialized, a couple of reasons why that could be the case. Null is intentional, and we need to be able to handle that null case depending on the domain logic that applies. The other one is it's an accident. Maybe the user entered a value where they were didn't enter one where they were supposed to enter one. Variable didn't initialize. Maybe we had some try-catch block that botched it somehow and swallowed an exception, and then a bunch of variables wandered around the JVM without being initialized, or rather, well, being initialized to null, but really that doesn't help a lot. So yeah, so these two big buckets. Now imagine you get a null-related bug. Could be null pointer exception, which are already the easier kind of bugs to fix because at least they yell at you what's going on. So the bad step to take at this point would be, oh, this was null? Oh, no problem. I'll just add a null check and move on. I don't know, not do the method call at this point. And if I need to return something, well, I'm just going to return null as well. That can be the right solution. But if that is basically the go-to solution, that is really bad. Because the proper solution would be, okay, first I have to figure out what the hell is going on. Where does this null come from? Does it come from an accidental absence or like a failure, or is it intentional? Is it allowed to be absent? And my personal experience with null and why I'm so frustrated at it is that this is the problem. Hunting it back to its source, that's the biggest step, specifically because everything in Java can be null, right? Well, not everything, but most things. So that could be quite a long path. I had situations where I worked on a project where there was some kind of registry, and occasionally some buggy module, like a central registry for services and information. And occasionally a buggy module would register null instead of the actual thing. But many modules could register that same thing. And that was really hard to figure out in what combinations of modules did this. This was horrible. Probably this was the thing that burnt me. So what I'm saying is following null back to its source. That's the challenging part, but that's the most important part. Then you need to determine whether it's intentional or accidental, and then you need to fix your code accordingly. So the problem with null is not avoiding the exception. The problem is figuring out what null really means. I hope I established that by now. So then the question is, what of these two are more work? Is it just avoiding it by adding a check, or is it to figure out where it comes from? And which of these two would the question mark dot make easier? It's the first one, right? It's just like, okay, let's not think about this too hard. Let's put this in. So this language feature applies in a situation where you have a choice, and it makes the wrong choice easier. That doesn't mean that if you actually tracked null back to where it came from and then decided that, yes, I can do the question mark dot here, that this can be the correct solution. And then it would make that solution much simpler. Those are definitely given. But I argue it will make it easier to do the wrong thing. And that is not something that, as a language designer, I think you're usually looking for. And that's why I like optional so much. Because I can distinguish the situations where something's allowed to be absent, then I use an optional, or where it's not allowed to be absent. If it's not allowed to be absent, then it's just a regular string or list or whatever. Well, I don't do optional of list, but well, you get my drift, right? If it's an optional, it can be absent. If not, it's supposed to be there. And if I write code bases on my own, null is never a legal value. So I bake this distinction, intentional versus accidental, into the code. But it doesn't work elsewhere. And they wrote that it works well in JavaScript. Well, I think it's kind of hard to draw conclusions from JavaScript to Java because there's a bunch of things that Java does that JavaScript doesn't. Like type safety, for example. And if you use TypeScript, then it's a different situation because in TypeScript, at least if you apply strict typing, then you have something that I'm going to explain about here as well, about Kotlin. Because Kotlin has this, and it works in Kotlin, right? So this is something that you can write in Kotlin, and they don't complain about it. It seems to be working really well for them. So why can't we have that? What's the difference? Well, the difference is that Kotlin doesn't just have this null-safe member selection thing. It has more than that. It has a type system that understands null. So if I write this in Kotlin and say, okay, I have a variable of the name street that is a string, And there's a customer that might be null, but if it's not get the address, and that could also be null, but if it's not get the street, then obviously this right-hand side here could evaluate to null. But the type string does not accept null. I would have to declare it as string question mark. So the type system understands that there is a thing like null. And if you put those two together, then this null-safe member selection makes null easier to handle. That's, I already said that's a given, but my complaint was it also makes it easy to spread null around the entire code base. And that's true of Kotlin as well. But on the flip side, Kotlin has something to, to rein that in. It has nullable types that require you to explicitly handle null. So if you're in this situation here, you have a street like this that is nullable, you can't just call a method on in Kotlin. It will be like, wait, you can't just call a method. That might be a null pointer exception. You need to handle that case somehow. So you have one mechanism that has a good property. It makes null handling easier in this case, but it also proliferates something that's not great, like, in this case, more null instances. But you have a second mechanism that you're supposed to use that works against that and requires null handling and minimizes it. So the challenge with null is, in my point, determining its meaning, and the null-safe member selection doesn't help with that. Instead, it makes the wrong choice easier unless you have nullable types to work against that. And so once again, I want to take a higher level summary, and it doesn't make sense to introduce something that makes the wrong action easier, but that it requires non-existing features that this specific ecosystem or language or API or whatever doesn't have to really work well. So just because something works well in one language doesn't mean it'll work well in another. That's really important to internalize. If you work with different languages, and some languages have something that you think is great, that doesn't mean if you take this thing out and put it into the other language, that it will work great there as well. It could. It's not like that cannot happen. Of course it can. But there's a good chance that it doesn't, that it does not translate well. And it's not only can it technically work, it's also does it align with what users are used to, with what developers are used to in that specific language. So why can't we have nullable types? The summary is kind of a bit like immutable collections. Like, they're not hard to introduce. It's just a really hard, like it's really, really hard to do it without breaking the language or breaking the ecosystem. But I mean, if you already split the ecosystem for immutable collections and we split it here again, and then some people wanted it to split on generics and others to split on the module system, hey, that's 4 splits. That's only one of 16 configurations that any given project can be in. That's surely going to go well. Okay, so as a summary, sometimes we look at features and think that would not be a bad feature to have. And then often we take it from there to saying, and that's why we should have it. But there's a long road from one to the other. So not every problem needs an immediate solution, particularly not if we already have acceptable solutions or a better solution exists in the future that would then be prevented. But even if, so also not every proposal that works in another language is a good solution. But let's say both of these are already past that. You decided or you realized, well, no, this is actually a good solution for this problem. That doesn't automatically mean that it's more important than the other things that the JDK team is working on, right? Because you know that from your own projects, you always have to prioritize what to work on. But even if it's important enough, so it would be prioritized highly enough, that doesn't mean that it can be retrofitted. It doesn't mean that you can introduce it in a language in a way that makes sense and that is worth taking the path from where you are to where you want to go. So for example, I personally think, oh, that's not good. I personally think that the module system was important enough to take some bumps in the road as a given. I would say that lambdas might have been important enough for that. Lambdas work really well, but even if lambdas would have required some certain backwards incompatibilities, I think they were enough of a big thing to introduce. But some of what I just presented, for example, immutable collections, surely aren't. They're not important enough to require, I think at least, this amount of work that would be needed. And so this was the steps that I wanted to basically, instill in you. Not a bad feature is not enough. There are many more hurdles a feature should pass before it makes sense to introduce it in the language. I know this has been kind of a negative talk because here are a ton of great things that you can't have, but I do have better talks as well. If you go to nipafx.dev, for example, there's a list of the talks that I give and a blog post. You can go to insight.java, which is a site that we at Oracle maintain, where you can learn about new language features and what's going on the mailing list. So there are a bunch of resources linked here. If you want to learn about the module system, I wrote a book about it too. So you can have a look at that too if you want. And yeah, that's it for me. Oh, by the way, I'm nipafx everywhere. So on Twitter as well. If you have any questions, you can always hit me up on Twitter. And yeah, I hope to hear from you. That was it.
I have a little question, actually, if that's all right. Kind of that summary slide that you have then, obviously, you're talking about the different potential features and ideas that might be nice, but we can't necessarily have without a lot of pain and complexity, I suppose. And then you mentioned module system. That was one of those things where the decision was made to take, embrace that kind of breaking change, essentially. Are you aware of anything else on the horizon that could have a similar impact in terms of that trade-off between it's worth kind of having that pain to bring in some new feature?
Yeah, I think the important part there also is to distinguish between things that are actually backwards incompatible, like introducing new list types and then changing some of the JDK methods return types. That would be an actual breaking change. When you take it that literal, the module system had actually very, very few of those. Most of the things that harmed us by adopting Java 9 is that we did stuff that Sun already started us we shouldn't do like 20 years ago. So there's a difference in like something strictly backwards incompatible and something that just can be a bit rough in the road because we've just done things that we're not really supposed to, that the Java platform did not promise us would stay that way. So that's why when I said, right, the module system, there were some things that were a bit shaky when it came to the migration. Many of those, as I mentioned, are not strictly speaking breaking changes. And this, I think, is the more common case in the future as well, where it will more often collide with something that, maybe we're not aware of, that should not have been exactly that way, that we coded something in a way that, for example, there was introduction of the keyword, of the word var, right? Java 10 introduced var. And var is not a keyword, so your variables, your methods, they can all still be called var. It's a reserved type name. That means it only has a special role where a type is supposed to occur. So if you have a type that's called uppercase var, a class, that worked. But if you have a type that a lowercase var, that would actually not compile. You would actually have to throw away that class or rather, rename that class. So in that sense, Java 10 introduced something that could have broken code out there, but rarely anybody has lowercase letters, or starts the type names with lowercase letters. So I think what we'll see is more likely around these smaller parts. But to your question, am I aware of any specific changes that break something? I think like Brian Getz works his heart out to make, for example, Valhalla not break anything. The same can be said for Project Loom by Ron Pressler. These are both deep changes in the JVM, and Valhalla also surfaces all the way up to the language, and I'm not sure about those. So there might be something. For example, Valhalla started to deprecate the new integer constructors, new double, new float. Those got deprecated because we want to use, we don't want to directly instantiate these wrappers anymore. So I think the large changes can have some of these impacts. And I think, for example, giving up the integer constructor for getting Valhalla is obviously a good deal. And I think that shows us on what level, like how much of a gain you must get for what little inconvenience so that it's considered worth it.
Yeah, nice. It's useful. Thanks.
We had a question about Java 17 in a couple of months. It will be interesting to see how quickly people upgrade. You wrote that, Nick. Yes, I'm really curious to see that as well. I think after updating to Java 9, specifically in the early months, was a bit of work. Many people heard about. I think many people got shied away from that. I think nowadays should probably be very comparatively simple update, and then stuck to Java 11 as the next long-term release. But between 11 and 17, there have been very few situations where a minor amount of code bases had some trouble. I think for the vast majority of code bases, they could have gone. That once they made it to 11, they could have gone every step of the way. So I really hope that the big feature set that 17 brings over 11 will bring most people that are in 11 to 17. I think there's very little reason to stay on 11. And then maybe a bunch of those projects, and I hope some of the people out there watching this will be among them, or will have projects among them, will be, you know what? From 11 to 17, it seems it has been workable, this 6-month release cadence. Maybe we can try with a project or two to do that as well in the future, because I think most projects would benefit from that, or well, all projects would benefit from that if you make this 6-month release cadence step. But also the ecosystem as a whole would benefit from that, because it would make it easier for the JDK team to get feedback on the features that they're developing, and would pull more people out of the past into the present. So I really hope that there will be. I'm more interested about Java 18 than 17. I guess many people will go from 11 to 17 very soon. I really hope that more people go from 17 to 18 than went from 11 to 12.
Yeah. Awesome.
Okay, is there any other further questions? I think there's something from James. One thought on immutable collections. If generics could support, that might let people create their own mutable things.
Well, record is its own class, right? Every record extends the class record. I'm not entirely sure. I don't have an IDE at hand right now. You should be able to write, I have an immutable list of E or T extends uppercase record. Like how you could write T extends object, which you don't because it doesn't make sense. But I think you can do that with record. So if you think that will help you, you should give that a try.
Okay, I think that was all the questions we had. So no one else has any more? Okay. Thank you again, Nicolai, for joining the Manchester Java community today.
Sure.
And thanks to everyone for attending. There's some links to the YouTube channel in the chat and an invite to the Slack group. But hopefully we'll get this talk up on YouTube as soon as we can.
Yeah, thanks again, everyone. And thank you, too, for organizing this and for having me. And I wish you the best of lucks up there in Manchester.
Yeah, and to you. Thank you.
Thank you.
Bye.
Bye now.
Thanks, bye.